Soundstripe.
Machine learning techniques and algorithms are used in almost every application domain, such as image recognition, object detection, and definitely in financial applications. More recently, machine learning techniques have attracted a lot of attention from both the academic and commercial industries due to their proven successes in all these various application domains. However, developing a useful machine learning model is a repetitious, complex and time-consuming process that must usually be undertaken by a machine learning expert. The machine learning expert is required to make a whole lot of different decisions at all different parts of the machine learning pipeline in order to ensure that the model will be optimal. Thus, machine learning is the process. Automated machine learning is the process of automating these different stages of the machine learning pipeline and taking the human expert and the decisions that he needs to make out of the equation. This automation has been shown to produce superior machine learning models. Time series is a set of real numbered values which record historical data. A popular example of a time series is the price history of a stock chart, or the history of your electricity usage in your house. It is very valuable to all different industries to be able to predict the future value of a time series. This is known as a step-ahead forecast, where certain statistical methods or machine learning methods can be used to predict the next step-ahead forecast, to predict the value of the time series at the next point. Another useful prediction on time series, which we will focus on in this research, is the prediction of trend. Trend is more concerned with the direction of the time series, whether it is increasing or decreasing. We have chosen to explore a sub-problem of AutoML, which deals with making the optimal selection for the machine learning model and its respective hyperparameters. More on this later. In line with the objectives of this research, we are investigating solving the combined algorithm and hyperparameter selection and finding the most effective optimization technique to do so. So now we will take a quick look at what exactly the combined algorithm and hyperparameter selection problem is. It is important to know that when a data scientist sets about to train a machine learning model to a set of data, there are many hyperparameters that he has to manually tune. The tuning of these hyperparameters on the machine learning model greatly affects the performance of this machine learning model. Choosing the optimal values for these hyperparameters requires expertise and is a long and repetitious task. Moreover, there are a wide array of machine learning models themselves that the data scientist can pick between in order to best suit the data. The performance of such models vary depending on the specific application domain. So now we see that the data scientist has a large array, a multi-dimensional choice to make of machine learning models and the hyperparameter setting to go along with that machine learning model. And all of these different decisions greatly affects the performance of the application. Combined algorithm and hyperparameter selection is a method of choosing the best combination of machine learning algorithm and hyperparameters. In this method, the selection of an algorithm along with the optimization of its hyperparameters are executed simultaneously and solved together as one black box optimization problem. Now that we have formulated the combined algorithm and hyperparameter selection problem and shown how it is essentially an optimization problem, now we can look at the different optimization techniques which we want to explore in our research. The main focus of our research, as stated in our objectives, is these two evolutionary algorithms, namely particle swarm optimization and genetic algorithms. In order to know whether these evolutionary optimization techniques were effective at solving the cache problem, we must test the same data for the same problem using benchmark optimization techniques. It is important to know that these comparisons are only truly relevant given the same amount of budgets, which could mean that they are given the same amount of time to run as the evolutionary optimization techniques, or are allowed to run for the same amount of iterations. If after a set budget we find that our evolutionary algorithms were able to find more effective solutions, then we can conclude the promising nature of our evolutionary algorithms.